Number 345, which is down here. Use Stokes' theorem to evaluate the integral of 1/2 y squared dx z dy plus x dz, where c is the curve of the intersection of the plane x plus z equals 1 and the ellipsoid x squared plus 2y squared plus z squared equals 1, oriented clockwise from the origin. So when I'm looking at this from the origin, I'm looking out, and if it's clockwise, that means it's going to be going in this direction. And because it's clockwise the other way, which means when I look at it backwards, it's going to be counterclockwise, which is what we use when we talk about this positive orientation here. So we need that clockwise. So now what we're going to do is we're going to talk about Stokes' theorem, because it told us to use Stokes' theorem. Now, one thing to consider here, when I deal with this formula on the right here, we've dealt with that quite a bit already, the f, plug in the rt, dotted r prime t dt. That's when I'm dealing with this curve. But now we're going to open it up, and we haven't used Stokes yet anyways, only two-dimensionally, and that's called Green's theorem two-dimensionally. But anyways, back to this one here. Now we're going to take a look at the two-dimensional or three-dimensional surface here. And we're going to talk about that surface for that integral now. So instead of thinking about just the curve here, we're going to talk about all of this surface area here. And that surface area is the one we're going to use on the left, and we're going to use the curl dotted with the normal in order to do that. So that is the amazing thing about Stokes' theorem, because I start with one side, I go off to the other side here, and then I realize that those are equal. So I can look at this as just as far as the curve, or I can look at it as the surface area. And that's the beautiful thing about this, is that they're equal. So now what we're going to do is we're just going to take a look at what we get right away. So when I look at the integral, instantly I see my f. So that's going to be the 1/2 y squared for my x. My y is going to be z, and my z here is going to be x. And I know that may sound a little confusing, and essentially, I should say p, q, and r, to be honest with you. Yeah, because we're beyond that now, so my p is actually 1/2 y squared. My q is z, and my r is x. And then just go with that. Now we're going to need the curl of that. So we're going to take the curl now of f. So here's our handy-dandy formulas. And again, remember, we're just going to subtract them. So r, and I'm just going to write the p, I should have left it here. Q and r here. So ry is 0. QZ is 1. PZ is 0. RX is 1. QX is 0. And PY is y. And just remember that all those RYs are partial derivatives. So then that tells us that the curl of f now equals, now I'm just going to put those together. Now keep in mind here, it is a vector. So I'm going to do 0 minus 1, so I'm going to get -1. And then 0 minus 1, that's a -1, but then I have to negate the, no, it'll be -1. Yep, it's already done in the curl. Yep, and then I'm going to get a y here. So that's my curl of f. So now I don't need these partials anymore. Those are gone. Okay, so now what I'm going to need is I'm going to need my RUV next. So I have my function, or my vector field. I have my curl of f, and now I need my RUV. And in essence, I'm just going in order here. I'm going to need my RUV to plug into my f, my curl of f, I should say. Then I'm also going to need it to find the normal vector, the tu cross tv. So let's do the RUV now. So in order to do this, we have to find out where these two equations intersect. And one way to do it is just substitution method. So what I'm going to do for this top one here is I'm just going to solve it for z. And I'm going to get z equals 1 minus x. And then I'm just going to take that and plug it in the other one. So I'm going to get an x squared plus 2y squared plus 1 minus x squared equals 1. And then I'm just going to simplify this as much as I can. So I'm going to get the x squared plus 2y squared plus 1 minus 2x plus x squared equals 1. Now just remember this. This is a FOIL here, so don't lose sight of that. Now I'm going to put my components together. So I'm going to get 2x squared minus 2x plus 2y squared. And then I'm going to move the 1 to the other side, so that's going to equal 0. So now what I'm going to do is I'm just going to divide both sides by 2. And I'm going to get x squared minus x plus y squared equals 0. And then I'm going to use completing this square for these two components here. So that means I'm going to have to take half of b, which is my negative x, and square it. So I'll be adding to both sides 1/4. And that's going to result in, I'll write it out, x squared, x squared minus x plus 1/4 plus y squared equals 1/4. And then this is going to be x minus 1/2 squared plus y squared equals 1/4. And really this is a circle of radius 1/2, and it's just shifted in the positive direction on the x by 1/2. That's what that's telling me. So it's nice to understand that for the sake of our RUV here. So I'm thinking cylindrical here, just because I'm seeing the squareds, the x squareds, and that's what I'm going to go with. So I'm going to say, hey, my u is going to equal theta, and my v is going to equal r. So then for my first component, my x there, now keep in mind here, this whole thing here is going to equal my x normally is x equals, we would say v cos theta. So that's what this whole thing would actually equal. So instead of x, just an x here, we're going to have x minus a 1/2. So what we're going to end up with for our x here is v cosine theta plus 1/2. Because remember, it's going to move to the right 1/2, and that's going to add a 1/2 to my x. So same idea here, but just in parametric. Now for my y is going to stay the same. That's just going to be v sine of theta. Oops, I should have u there, not theta. I knew that sounded weird. So that's a v sine u there. And then for the last one, we're going to have to think about, our z is just usually equal to z. That's how cylindrical works. But what we have here is we have this z equals 1 minus x, and my x is v cosine u plus 1/2. So this is really going to be 1 minus v cosine u plus 1/2. And if you think about this negative being distributed here, it's really a minus 1/2. So we're going to end up, a positive 1/2, we're going to minus a 1/2, but we're going to end up with a positive 1/2. So this is just going to be 1/2 minus v cosine u. So there's our RUV that we have now. Now we have to think about our next step. Now just remember, the order in which I'm doing this doesn't always have to be the same here. I'm just going as the formula presents itself to me. So I can plug in that curl of f into the, plug the RUV into the curl of f there. So I can do curl of f equal, I should have the notation there at least. And that's going to equal -1, -1, and then my y, which is v sine u. I almost forgot to put my negative in there. So I'm going to move that over, put my negative in. Okay, now I'm ready to roll. So that's my curl of f with my RUV plugged in. So now we're going to find the TU cross TV. And I'm going to do that on the next page because it's going to take up some space. So I put the other information over here just to know what we need. So now I'm going to do the RU. And RU is, here's my RUV here. So R with respect to U for the first component here, it's going to be negative V sine U, comma. And then for the middle component with respect to U, it's going to be V cosine U, that's here. And then the derivative with respect to U for the third component, that's going to be minus a negative, and that would be here. So that would be, V sine of U, positive. So that's what we end up with here, and that's going to be our RU. Now for our, so then for the RV, that's going to be cosine U, comma, and sine U for the middle term. And for the last term here, it's going to be negative cosine U. There we go. Now we're going to take the cross product of those two. So then the cross product is going to equal, I'm not sure I'm going to have enough room for this one. It's going to be a long one. So there's the first step. You can pause it if you want and review it, but that's where we're at with this. And I'm just going to clean this up a little. This can definitely be cleaned up. So this right here, I can pull a negative V out of both of those, and I'm going to get a sine squared U plus a cosine squared U. So I'm going to get a 1 there. So this is going to turn out to be just a negative V. And the middle, as you can see here, they're the same and they're subtracting, so they're going to cancel each other out and on with the negative 0, which is 0. And then for the last one here, I can do the same thing I did like the first one. I can pull a negative V out of both of those, and then I'll have sine squared U plus cosine squared U. And that's going to also equal another negative V there. So that's what we end up with when we do RU cross RV. And we end up with negative V0, negative V. And that's our N there. So now what we're going to do is we're just going to take a look at our surface here and make sure we're going in the right direction. Now we just have to make sure that our normal vector is pointing in the right direction. So if you notice here that it's actually pointing in that downward direction is really where we want it to be, because that's where it was told it was going clockwise. So we want to make sure we're in that downward position, and we are. So our N checks. Now we're ready to set everything up and put it all together now. So here is our formula here. So I'm just going to write that down below. We have our curl of F here. So we're going to write that down below. Well, double integral first. We'll worry about bounds in a minute. So we'll talk about that after our setup. Okay. Then we're dotted. And then we're dotted with our N, which this is our N here. And then we have du dv. Now let's look above here. Remember when we had these parameters here, it told us what u was. U was between 0 and 2 pi. So, because are we going all the way around though? That's the question. Are we going all the way around to 2 pi? And we are, because we're coming out and we're going all the way around still. So that doesn't change. So that's 0 to 2 pi. And now we need to talk about our V. Our V is our R here. And do you remember where we get our RUV from? It was the equation. It was this equation here. And that equation says that my R then, my radius was actually 1/2. So this would go from 0 to 1/2 for my V. Now I should have wrote that down right away. From now on, when I write my RUV, I'm definitely going to write those parameters down right away so I don't lose track of them. Because that was quite a while ago when we came up with this this equation here for to get my RUV. So now we have everything we need and we can actually integrate this thing and do what it was asking for. So I'm just going to write the answer for this. You can go through the dot product and whatnot and get this simplified. This is an easy problem to do by hand, but I'm not going to waste any more time because we're already almost at 15 minutes. One thing I will do is I'll actually do one more step here. I'll do the dot product. I think that's fair because that's going to VB plus, and that would be 0 for the middle terms. So I'm not going to worry about that. Plus V squared sine U du dv. And I just did that for the sake of, oh, here it is. This is what it is. So now we can actually integrate this. After I put my other bounds in, 0 to 2 pi. There it is. Okay, got everything I need now. And then I'll punch it in my calculator. And our final answer is pi fourths. So there we go. That's all of our work using Stokes' theorem.